Hey, good afternoon, everybody, or good morning, depending upon where you are. Welcome back to another Takeo Tuesday extravaganza. I'm John Barba with Takeo Comfort Solutions, joined by the two best trainers I know in this industry, Dave Holdorf and Rick Mayo. How you doing, guys?
Yeah, very good.
Thank you all for being with us today for another edition of Takeo Tuesday. And as the sign says, we have a terrific program for you. Again, one of my favorites. It's going to be on ModCon boiler piping and most importantly, ModCon boiler pumping.
Pumping.
And taking care of the duties today is maybe the best trainer or presenter on this particular line of information that I've ever seen, and that'd be Rick Mayo. So Rick, I'm really looking forward to your presentation today, and I hope everybody else out there is as well. A couple of things, again, just to get us, if there's a lot of first timers out there, I want you to understand the control panel basics, particularly how to ask questions. So if you take a look at the control panel, you should see a little orange arrow on the right hand of your screen. If that arrow is pointing to the left, that means the screen's minimized, so click on that and it'll expand your control panel. And the upper portion you'll see is the audio section, just to make sure you get the right speakers selected, etc. There's also a section for downloads. We do not have any downloads for you today, but in future ones we most certainly will. And finally, down at the bottom is the most important part, and that's how you're going to ask questions. And we do encourage you folks to ask as many questions as you feel as you want to during the course of this hour. One of the things we do at Takeo is we don't ask you to hold your questions till the end, because that's kind of lame. What we'd like you to do is ask them as we go along. Okay, ask your questions as we go along, and we'll take a break every few slides to start to address some of the questions that you have, and we'll stay on at the end as long as you guys have questions. We'll stay on as long as we have answers. So. So we will be available after the class for as many questions as you have. If you could all do me a favor right now, just to know that everybody out there kind of knows how to do this, could you just type in a hello, how are you, whatever it is you have in that question chat section, so I know that you know how to do this, and I know that you can hear me. That's the other important thing. Okay, very good. We got a lot of hellos. Excellent, terrific. You guys got it. And please make sure just type in your questions as we go along, and we'll be able to really make this a really fun and interactive as possible in this webinar setting presentation as we can deliver. Now, if you happen to be on like a tablet or a phone or something, it's a little bit different. Just down at the bottom is your control panel. You have a little screen toggle where you can go back and forth between webcams and presentations. Your audio settings are there, and that little question mark, obviously, if you press on that, that'll be how you can type in a question for us. So just so you have that all set and ready to go. And with that, without any further ado, I would like to turn it over to Rick Mayo. Rick, I'm going to hand you the con, and you can take it away from here.
You tell me when you can see my screen.
All right, I'm going to make you the presenter. There you go.
Show my screen.
Hot diggity. There it is.
There it is. Thank you.
All righty. And
all right,
both Dave and I will visually be saying goodbye, but we'll be right here to help out with the questions.
Visually. Okay, cool enough. Let's go ahead and jump on in. Thanks for the introduction. Thanks for everybody showing up. And this is a topic that is near and dear to my heart, but most everybody in the hydronic heating business as well. So I will say this as kind of a preface as we get into, what we're talking about. We're doing this for a reason, right? And one of the things I hit a bunch of slides that were the first part of this presentation, but for the sake of time, right? But one thing I didn't want to not convey is the importance of low temperatures back to a condensing piece of equipment. In this case, we're talking about condensing boilers, right? So, there's the magic number, right? And I guess my point is this: I want to make sure you realize that there's a goal we're looking for here. It's low temperatures back. If you look at this chart that comes to us, I've seen this from ASHRAE, and almost every boiler manufacturer out there that sells condensing equipment uses something that looks just like this or similar to this to some extent. But you notice there's this magic spot in which the pitch of this curve changes quite a bit, right? And this spot here, it's pointing out that it's 135-degree dew point for natural gas flue products. But that's not the number we're looking for. That just tells you the science is happening back inside the combustion chamber and stuff. What we're looking for is a fluid temperature that's low enough so that the surface temperature can actually see condensation. So we need low fluid temperatures, and a lot that has to do with a couple of things we're talking about here, like John already mentioned, piping configuration and pump sizing has to do with getting this efficiency up where it belongs and keeping it that way, maintaining it, sustaining it, etc. So why don't, since I can't see the answers, I'll depend on John and Dave to give me some feedback. Who wants to throw out a nice round magic number for the return temperature back to a condensing boiler? Go for it.
We got a couple of folks who did not hesitate whatsoever with those numbers. I have everything ranging from 130 to 100.
Oh, okay.
We got a 160 in there as well.
Okay. Well, 130 is the magic number. It's round. It's rounded, I should say. And of course, down here, keep in mind, the lower the better. So whoever's talking about 100, yes, amen. That's what we're looking for. So again, I just wanted to preface that this is what we're doing here. Now, one of the things that comes up is how do you pipe a condensing boiler? Now, you pipe it the way the boiler manufacturer tells you and shows you in the back of their book. All the back of their books are really good. They're getting even better from 20 years ago when I was kind of messing with this quite a bit, as far as giving you more information. And so some of the things I'm going to talk about are generalizations, but always refer to the boiler manufacturer's manual. They'll give you what they want and why they want it, hopefully. But since a lot of those manuals tend to talk about piping in a particular configuration, we're going to focus on that, and that, of course, is primary secondary. Well, primary secondary when we're talking about boiler piping has to do with the separation of the circulators within the system. Now, the one that's on the boiler should only be affected by anything that's in the circuitry of the boiler. That means the heat exchanger, the near boiler piping, the closely spaced T's, the hydraulic separator, etc. Okay, that should be its only worry. And then the system circulator or zone circulators that are on the secondary side, those should only be affected by what they're responsible for. So it's actually just separating the lines of responsibility and making sure that circulator is only doing what it needs to do. Again, this came up in one of our other sessions last week. We were talking about low loss headers, use that in quotations. And where did that term come from? Well, that term came from a device that kept the pressure drop of the heat exchanger of the boiler out of the responsibility of the system circulator. Okay, and so it gave us some of the things that we're looking for. We're not going to focus on that so much today, but we call them hydraulic separators or low loss headers, but that's the reason it was called a low loss header, because we didn't want the pressure drop back in the early days of condensing equipment, which was relatively high, to be the responsibility of the system circulator. Okay. So anyway, the boiler manufacturer nowadays can and may control the primary circulators, that's the boiler circulator, that can control its speed. We'll talk about that a little bit as well. And it's actually, if we can do that, we want to do that and take advantage of that as well. One of the downsides of primary secondary piping is you have the possibility of short cycling water from the supply pipe that goes into the closely spaced T's backwards, I should say, and back up and into the boiler. And this will happen on some occasions. What we're trying to do with this little session is make sure you keep that to a minimum. okay? And we'll show you what that looks like. This is just words on a bullet right now, but we'll get into that. We'll talk about what that really means, okay? And again, refer to the boiler's manual. It shows you what they want, what's acceptable, what's not acceptable. One thing I will throw out with this in mind, if the boiler manufacturer allows you to pipe the boiler in series, that means not primary, secondary. Some people call it direct flow or variable primary, or there's some other terms out there. If they allow you to do that and your system affords you that opportunity, then by all means, do it. Then some of these things that we're talking about in primary, secondary don't need to even be considered at that point in time. But there are some caveats to that. So that's why I say just follow the boiler's manuals, boiler manufacturer's manual, and you'll be safe, okay? Let me ask a question. Give me some quick feedback. Anybody pipe like this anymore when we're talking about condensing equipment, okay? And I'll call this a boiler loop. Okay, that's where boiler, you come out of the boiler, you make a nice big halo or a big loop, and then off of that you do your closely spaced tees, and you take care of your highest temperature first, next highest temperature next, etc. Anybody out there still piping this way? It's kind of a throwback to the early days of getting multiple temperatures on a traditional cast iron atmospheric boiler, but some people have taken that concept and kept it with condensing equipment. Any answers out there, guys? Anybody, anything coming in?
I have one and one emphatic no, and then one occasionally where requirements are correct. We got a not anymore, we got a no, and a no uses separator near the tank. And then we have a yes working with an engineer now that refuses to change it. So
Okay.
we're kind
All
of all
right.
over
Well,
the map there. So yeah,
we're
okay,
all we got a mixed bag, as they say. Very cool. So I'm not going to elaborate on this. I will say that we're still talking about boiler circulator sizing, right? We're still talking about closely spaced tees, and all that applies. Okay. Here's what we typically see nowadays. Most of the boiler manuals out there, they're showing, for instance, this is depicting a wall hung condensing boiler. This is kind of how they show it. We have the near boiler piping, which is just relatively short. It just comes down and goes into the secondary portion of the system, right? So again, we're going to focus on these two things here. We're going to highlight this. It will be a little bit of review because we talked about this in the last couple of episodes of Takeo After Dark, and that's a plug for Takeo After Dark for those who are sitting here for the first time and haven't heard about Takeo After Dark. It's an evening session. I'll let somebody elaborate on that later, but we talk about things like this, and we might get into a little more detail. But one thing that I mentioned on one of my bullets is the ability for the boiler manufacturer now to have control of the circulator. So what I'm saying is a pump manufacturer like Takeo now gives the keys to the boiler manufacturer. Here's the keys, you run me however you see fit. And we're doing that with typically in North America 0 to 10 volt DC signal down to the circulator. This is not just powering the circulator, it's saying, look, I'm going to power the circulator and I'm going to control its variable speed based on input that I'm receiving from something that's within the boiler manufacturer, right? The boiler manufacturer always is looking at supply and return temperatures across its heat exchanger. It also, in some cases, has the ability to look downstream, maybe put a sensor out over here and look at the secondary portion of the system. Okay, the system side of things. So again, understand that that's all information that the boiler's making decisions on, and it now has the ability to ramp this circulator up and down to maintain something. The majority of the people that have had success doing this, that input is based on a temperature differential across its heat exchanger. Okay, we know that as a boiler modulates its flame up, we're adding more energy to the fluid within the heat exchanger. Well, the telltale sign of that is a big increase on the supply water temperature. So if it sees a delta T that starts to widen, that's its signal to say, hey, if it goes beyond what you want it to, and it says, hey, giddy up, pony, let's get some more pumping going on, and let's pull that energy out of the heat exchanger and send it into the secondary and tighten up that delta T. Okay. And on the other side of the coin is, hey, if we see delta T's that are too tight, tighter than they should be, then let's slow that circulator down and let's get back into a lower return temperature and kind to stop that that water coming across these two T's that I spoke about earlier, right? And I'll get into that anyway. Understand that if you have the ability to do this, this is a good thing. The only issue, and Takeo makes circulators in the kind of the mid-range size and the light commercial size that have 0 to 10 technology. Most everybody, and including us, they're little tiny pumps. In our world, it's a little 44-watt circulator. Currently doesn't have in an ECM offering the ability to have that 0 to 10. So what my next slide is going to talk about or just touch on will tell you why we're still talking about things. Otherwise, we just say, always do this. The problem I see out there, especially with some other products that come packaged with some competitor product on it, is there's an old saying out there, you can't go any lower than low. And if you put a circulator on there that has 0 to 10, but is physically too big of a circulator for the job it's being asked to do, then it just kind of sits there on low speed. It can't go any lower, and therefore it cannot widen that delta T any more than low speed. So a lot of you know where I'm going with that, but maybe I should open it up if there's any questions as it relates to that. And if not, I'll continue on. Anything out there, boys?
Here's a quick question from Carmine. What is the valve shown below the circulator, below the boiler circulator in the system piping?
Right there, would it be this?
Yeah, I think that's what he means.
Oh, okay, that's a magnetic dirt separator. That's our 4900 series magnetic dirt separator. And that's just to protect everything that's going back to the boiler in this right there. Okay, so hopefully that answered that question. Yeah, I wouldn't think this is just an isolation valve. This is a check valve that just happens to be part of that circulator package, and another isolation, a boiler drain. So I think that's what you're talking about right there.
Yep, he does, and he said thanks.
Okay, cool. Let me go back. So the reason, notice no more control wire. It's very important now to get this circulator size correctly. And we will talk about that. We'll give you some hints and some things to in some cases, kind of changes the way you've been thinking about things. I know others have noted that and just saying, yeah, I've been oversizing that pump. Well, that's what these seminars are supposed to do, is get you to quit just doing the boilerplate stuff, right? Start thinking about what you're doing and why you're doing it, and be able to back up, why you're doing what you're doing. And that's what Takeo's trying to do here, trying to make sure you have a better understanding of why you do what you do and why you size the way you do, et cetera. So we'll focus on this circulator. I will say this while we're on this slide, that the mode of operation, remember these ECMs have all kinds of modes of operation. Well, the only thing that makes sense in this near boiler pump application is that 0 to 10 or 4 to 20 milliamp, or there's some other things out there that's being done, pulse width modulation, some other things. One way or another, if you have that control, fine. But if you don't, there's only one other mode that makes sense, and most every ECM has it, and it's called fixed speed. Some people call it constant speed. But what we're saying is there's nothing within this circuitry. If you look at it, there's a boiler's heat exchanger, there's some piping, there's a T here, that's the circuitry that's responsible, that this circulator is responsible for. There's nothing that's going to give it a hydraulic change so that it would have the input to make a decision to speed up or slow down. So do not use an automatic mode for that pump. Okay, it just won't ever get the information to change its speed. It may or may not be enough. Now I'll show you one application where we're going to say, go ahead and do this, but it's only once you've dotted your I's and crossed your T's, and we'll show you that, okay? By all means, it's being done, it's done successful, but just, it doesn't make a lot of sense if your expectation is that the pump's going to speed up and slow down, because it will not. Okay, primary, secondary configuration, a little bit of review. Like I said, we've done this a little bit this year already. So again, I can't just assume that everybody that saw that is going to see today. So I'm going to talk like it's fresh and new and all that stuff. But it is the rules of primary, secondary piping in a condensing boiler application specifically. It's as easy as ABC, right? So what are the rules? These are, again, we always trying to get you to understand concepts more than numbers. You know, we always talk about doing the math and we show you numbers, you know, ad infinitum, right? But ideally, I think it's better if we can leave you with a concept that just sticks in your head. The concept is good. If you have the concept down, you won't ever have to worry about the numbers. That's not to say that the numbers aren't important. It just means if you're like a lot of people, especially service guys, plumbers, and things like that, once they get a concept down, that it's locked in. They might not remember all the little specific rules and stuff, but the concept works. So again, we're going to try to get two things accomplished here. Make sure that you understand the concept more than anything, and go ahead and give you the rules. Just if you want to take notes, as we like you to do that, and we like you to clarify and question and things. So let's go with that. So this A right here, this is depicting the distance between these two T's, right? And some people have said, well, is it on center or is it edge to edge? And you know, it doesn't matter that much, okay? And for the most part, it's edge to edge. How much length does this short little piece of pipe need to be, okay? Now notice this too, this says maximum. When it says maximum, don't pull out a ruler and cut it that length. Because again, the concept is get this piece of pipe as short as possible, right? You want that piece of pipe to be as short as it can be, literally, to make up those two T's that are closely spaced. Okay, so and we're talking about here not inches but pipe diameters, and it's of the pipe that's on the secondary side. In this case, the boiler's coming in and back up into this portion of the system piping, right? So what size is this system piping, the secondary piping in this case? You know, whatever you want, if it's 1 inch, etc. So it's easy to do math, okay? Don't exceed 4, but actually make it shorter than that, okay? The closely spaced T thing here is, this is something we do, and I think my camera is the only one that's on right now, but if I put my hand up and I say this is 1 T and this is 1 T, and I put those two T's together, and it's right in the middle of a nice long piece of pipe on each side of that T, right? I'm doing really good. That's the concept. That's what I'm shooting for. So anybody that wants to join me and won't be embarrassed sitting in your office doing this with me, they'll want to say, hey, is that just 2 thumbs up? Well, you could call it that, but it's closely spaced T's, and a good way of understanding that concept and keeping it with you, okay? Of course, that leads us to the B note, okay? Now, again, I've got an arrow here to show you what I'm talking about. From here, going this direction, from left to right. Now, the minimum amount of pipe diameters is 8 coming into this first T, okay? And we'll show you on this next slide a little more detail on that, but here's, you know, I'm giving you the concept and I'm giving you the rule. The minimum is 8 pipe diameters of this secondary pipe. Okay, remember, and as close as possible here, but downstream, since we've already done the job that we were meant to do by getting this water mellowed out, and I'll show you what I mean by that in a minute, then once we've done that, then we only need about 4 pipe diameters on this second side as a minimum. Again, conceptually, 2 T's in the middle of a nice long piece of pipe, okay? Understand that concept, you'll stay out of trouble. The C note here is just actually having hotter water higher than the water, so you get some thermal trapping going on. And again, that's kind of a throwback to the variable speed injection mixing. We're not going to spend any time on the C note, but just try to remember that the hotter water needs to stay higher than the cooler water in mixing primary secondary. Okay. Here's just some words out there, right? I got, you can see I've got what's depicting smooth flow and a chaotic flow. And some people would say what? They'd say chaotic flow is turbulent, smooth flow is laminar. Well, you could use that terminology if it works for you, but if you really look up turbulent flow and laminar flow, it doesn't necessarily fall into this category. So there's just terminology, so I changed it up a bit. But notice this, if I come out of this circulator downstream right after here, I'm going to be in a chaotic flow pattern because of what the circulator did by adding that mechanical energy to the fluid, right? It's going every which way. But once it goes out on this straight piece of pipe for a certain amount of distance, then it goes from this chaotic flow back to a nice smooth flow pattern before it gets to this first tee. This is what we're talking about right here. And again, this is nothing that TACO has done. This was done years and years ago in the mid 50s. Guys in white jackets in laboratories testing this stuff with pressure gauges and temperatures, and all this stuff's been established a really long time, but well before I was born, and I'm an old man now for the most part. So again, this stuff works. Once we get enough straight pipe, uninterrupted pipe, then it goes from one flow pattern to another, and that's what we're shooting for. We want a nice long straight piece of pipe before this first tee. Okay. Now there's been talk, well, how much distance do I need here? Well, if I've already done the job, I can actually butt these up. There's been some pre-assembled panels and some things like that have been sold for years and years that never followed, B plus B again, right? They were right up, and it works pretty good. So again, if you remember the concept, if I can make this longer, then by all means make it as long as you possibly can. If you wanted to do 4 pipe diameters and 8 pipe diameters for a total of 12, by all means do it. Okay, it would be a good thing. And hopefully that makes sense. And if there's any questions on that. So just a little review here on pipe sizing, right? We're just talking about the maximums that are out there. And again, whenever you're talking about pipe sizing, you should probably just figure out which pipe you're talking about, what type of pipe and what size is it. In this case, this little chart just referencing type L copper, okay? But notice there's a couple different columns that say maximum. Notice maximum, maximum. This one is 4 feet of head per 100 foot of pipe, and this is 4 feet per second. Those are 2 different ways that we look at maximums in our industry. And just again, since this is review, a lot of you folks have seen this before, but just the idea is doing the right pipe size helps quite a bit, especially in overall pressure drop and things like that. Remember that typically down to 1.5 inches covers us up to most residential applications, and starting at 2-inch and bigger would cover most of our commercial range, right? So notice one thing that's significant about these maximums. Right where the colors change here from green to red, and residential goes to commercial, it also flip-flops in the amount. Notice this column gives you more flow than this column until you get to 2-inch, and then this column gives you more flow capacity than this column does. So no, you guys that are out there doing work that kind of goes into commercial, just remember where you can flip-flop to your advantage, okay? Use what's within our industry's acceptance that is to your advantage. And when you remember things like this, it helps out quite a bit. So,
Rick, we have a question.
Go ahead.
Sorry, we do have a question about boiler piping and system piping. Can they be the same size?
They can be the same size, especially if you go back to where we were talking about piping in series, right? So that way the total flow of the system is going through the boiler. With that in mind, you would want the same pipe size. What we see in primary secondary quite a bit is that we're using a bigger delta T across the boiler side so we can get by with smaller pipe sizes. For instance, we might have 1-inch headers coming off a condensing boiler that go into an 1.5-inch secondary system piping. Hopefully that answers the question.
Right. And oversizing the system pipe, that oversizing the header is actually a good thing. It simply aids in hydraulic isolation.
It does on that close a near boiler header
Right.
for multiple zoning. Absolutely, that's your near boiler piping secondary header, and it wants to be generously sized or copiously sized, however you want to say it.
Well, they can be like me, short and fat.
Yeah. Well,
There
if
you
you
go.
want, if you want to go back and look at it, when we talk about, excuse me, this right here, if you keep those secondary headers in and around 2 feet per second, that's kind of a heads up that keeps them nice and copiously sized. Okay, so
There you
use
go.
your 2 feet per second on that close near boiler piping header for multiple zones, and then use 4 feet per second for your maximum velocity out on those secondary pipes or anything. Generally speaking, this would be your maximums. So.
Yeah,
And that's all this slide does. It just remind you, if we stay between 2 feet and 4 feet per second, we're in the sweet spot, folks. You'll stay out of trouble. Again, it's got to apply to the pipe and type that you're using, but it keeps you out of trouble. And this is just showing you at a given delta T, what could you transfer at this maximum. For instance, if I had a 1-inch pipe and I ran 10 gallons a minute through it at a 20-degree delta T, what should that be? Right around 100,000 BTUs, and it
right.
is. So just
Right.
understand that. But let's look out. Let's say that we went out to a 40 on a condensing boiler. Hell, I could do 200,000 BTUs. Now you might not want to do that, or you might, depending on how good you feel about what's written in the boiler's manual, etc. I'll refer you back to that every time. So
Right. In reality, it's impossible to oversize a header within reason. So yeah, if you want to, if the flow rate says 1 inch and you want to put 1.5 inches, it's only going to be of benefit to you.
yeah, it won't hurt you much. The only thing that would come to counter that, not counter it, but just say, hey, remember that we want to keep our at 2 feet per second
Right.
or slightly higher for the bubbles and et cetera. But again, folks, I get into this. I talk about if you do a good job of purging the big bubbles out, doing a really good job of the initial purging, the micro bubbles and the little tiny bubbles aren't what really hurt us a lot. It's the big, when we get a call and say this pump's not working or the boiler's going off on high limit, et cetera, it's because it's full of air and no one did the initial purge. They think just filling up the system, they think like in our case, the 4900 does all the work for you. No, it doesn't. You have to do the initial purge correctly. So anyway, so this slide just is focusing on the sizing of this near boiler pump in a primary secondary configuration and how that helps us in the overall boiler efficiency. And you folks know kind of where I'm going with this one, especially how I ended it there. You have to read the manual, and the manual is what will tell you what to expect as far as pressure drop is concerned from the boiler's heat exchanger. Okay, and I can't overemphasize this. Don't oversize the boiler circulator in a primary secondary application. Okay, it's not good for anybody. Okay, anyway. So let's focus on these two T's right here, okay? And I'm going to show you visually what happens, okay? I'm just blowing up those two T's, showing you what the ideal flow pattern that we're looking for, because we want the coolest water temperature to go back to the boiler. And if you're looking at this from the standpoint of with that understanding, you're going to surmise that if I've got water going up here and I have water going this direction, and I have this blending back in here, then this GPM is going to be equal to or slightly less than this GPM. And we're just splitting the flow here. But the idea is I don't have any of this heated water coming back across the top and coming in here. So that's why we say this is in a primary secondary configuration, this is the ideal flow pattern. We'll give it a thumbs up. Okay. Here's an acceptable flow pattern. People go, what do you mean by acceptable? That looks perfect to me. Yeah, but if I have primary secondary piping configuration, I have a dead space right here. Why do I even have it, right? The other thing is people say, well, I've got two pumps on there. What if I just make the pumps the same size? Won't I get this? as an end result, and I'll say, well, it's really hard to do. It's acceptable, but just not very practical, right? The idea or the concept of saying I'm going to put two pumps that are equal size and I'll get equal flow just goes against everything we teach you about pressure drop calculations and understanding, how something within the fluid flow impacts the pressure drop. So I think most of you can give me an understanding on that. It's really hard to do without doing balancing valves and all this other nonsense. So anyway, just understand that. Here's what we don't want to happen, right? Here's the thumbs down, right? So you can see this. It kind of shows you that if I oversize the boiler circulator, I have more flow going back across here and now blending that cooler water with a heated water, and now I'm reducing the overall boiler efficiency and the overall system efficiency. So that's undesirable. Now I will admit, I'll have to say that under these shoulder conditions, these bench conditions, where you just have really not really cold weather, just kind of sort of cold, maybe in the spring and in the fall, etc. You're going to get this a little bit because, as I said before, even if you have a circulator that is controlled by the boiler, you can't go any lower than low. And the thing that we have going for us in those shoulder conditions is that they tend to be not really cold. They're nowhere close to a design condition. And so they're relatively short periods of time where we have this. And the cumulative temperature is still below that magic number of condensing. So I'm still condensing for the most part within those shoulder conditions. So, John, is there any questions on that? Usually, that could bring up some understanding or clarifications or something like that.
One
Otherwise,
question, there was one question about would that not induce short cycling?
oh, absolutely. If depending on what that temperature is and how far that boiler was able to turn down or not, right? So different boilers, different things. But yes, good point to make. We're not only talking about overall system efficiency, but we're talking about steady state efficiency. We really don't want that boiler banging on and off, and that's a whole nother webinar that we'll probably do down the road when we talk about buffer tanks and things like that. So.
Did have one other question about the for closely spaced tees. What does the up to 12-inch max refer to in 4 pipe diameters up to 12 inches max?
3-inch pipe. And
Yeah.
how many people are doing 3-inch pipe on this webinar right now? On a regular basis, your boilers have secondary headers that are 3-inch.
That would be the 12 inches, right? 4 pipe diameters times 3
Yep.
inches, 12 inches. So again,
Yeah.
closer the better.
Closer the better. Yeah. Like I said, the problem that we see with the boiler manufacturers putting that note in there is because you take a fitter that doesn't understand the concept. Again, why you're sitting on this webinar, if you don't understand the concept, you're going to pull out a tape measure and you're going to cut a piece of pipe 12 inches because it says it right there in the manual, or it says it right there in the print. So again, the concept will save you time and money and headache. And again, the 12 inches that they note in those books primarily are talking about maximum spacing. If the concept is that I get it as close as possible, yeah, I think you'll get where we're going with this. So anyway, so let's use a boiler model that's around 155. Now I've hidden a bunch of slides for the sake of time of different manufacturers. I just picked another one that I haven't used in a while, and I'm talking about Well-McLean. You can see that down here, and this is what their chart shows for their condensing product. And my point is, I'm still emphasizing the fact that you don't want to oversize the boiler circulator. And again, these manufacturers will make it even easier for you to do this if you just read the manual, okay? But I'm going to generalize some things as well because you might not have the manual in front of you, or I might be able to emphasize the concept a little more here. So what is the range that that means the boiler manufacturer, will allow? The concept here, folks, is go as far as they will allow you in writing. That way your rear end is covered and you're not getting yourself into trouble, right? So in this case, they're showing you a 20 degree, a 30 degree, and a 40 degree delta T, and they're giving you following information based on that. What to expect for flow, your initial thing you need for sizing a pump, and then what to expect on the pressure drop through the near boiler piping and the heat exchanger in this case. So I'm going to show you what that looks like. These are the charts we're talking about. This is what you need to be able to comprehend and understand and how to interpret this, okay? Those numbers I just showed you are referencing flow through the heat exchanger based on GPM. Notice this is a little over 7, and at a little over 7, you're only going to have a 1.5 foot pressure drop, okay? That's relatively really low, but what delta T is that? Anybody want to guess? For the sake of time, I'm going to go ahead and throw it out there. Okay. So I'm just going to do a ladder here, right? I'm going to show you what it looks like at a 30. I'm going to show you what it looks like at a 20. Okay. Again, nice round numbers here. I mean, if somebody wanted to do a 25, you could extrapolate and come up with a GPM and that. Here's one thing I do want to point out. Some boiler manufacturers, including this one, will actually throw a little fudge factor in there. It's not really fudge factor. They're actually anticipating a certain amount of piping, valves, fittings, apparatus, incidentals on that piping that gives you a total pressure drop through the heat exchanger. Now, if you ever just don't put the belt and suspenders on here, right? If you know they make this note here and they're mentioning near boiler piping, then don't add additional pressure drop for that. It leads to circulator oversizing, just like we always talked about. So just remember what manufacturer, look and see. They'll normally say this is the heat exchanger only, or in this case, flow through the heat exchanger and near boiler piping is what this number here is. And you can do a comparative, like maybe I'll throw 3 or 4 different boiler brands out there, look at their 150,000 BTU model. Relatively speaking, they're kind of the same heat exchanger. And then you can look at the differences in pressure drop, and you can kind of tell which one's thrown some additional resistance on there for the near boiler piping and the ones that haven't.
So Rick, let me just clarify. You're saying that the boiler pump for a 155,000 BTU ModCon boiler, if my design delta T across that boiler's heat exchanger is 40 degrees, that boiler pump only has to be able to provide a shade over 7 gallons a minute at a little bit less than a 1.5 foot of head pressure differential.
That's
Is
right.
that what that's saying?
That's what that's saying. And got to always remember this, and only at a design condition.
Mm-hmm. Mm-hmm.
Okay.
We can see how really easy it is to oversize a boiler pump now, to the point
Absolutely.
where it is now to the detriment of that boiler's operation.
It is. And that's why the boiler manufacturers are finally putting this information in their manuals, because they get it too. Here's the thing, the boiler manufacturer, I'm sticking up because I used to work for one, right? I'm sticking up for these guys because when they sell you a packaged boiler, right, and they put a pump in there, that pump most likely is oversized. You know why? Because they have no idea what you're going to do with that assembly. They don't know what's happening on the secondary side, or if there's even going to be a secondary side, or if you're just going to use it for domestic hot water generation, et cetera, et cetera, et cetera. So they're just going to kind of, just take a guess at what will cover them for most applications. And that's why you see the packaged boiler pumps tend to be oversized. Believe me, most time, even when they give you a 3-speed pump, there's a lot of times that speed 1 is even bigger than it needs to be. And John's emphasis, I think, shows you that. Okay, there's a reason
Exactly.
John brought that up. He's seen this presentation before. He's making points here. Anything else that we cover, John? Any questions? I mean.
Nope. You can continue.
Okay, as I just showed you in the manual, right? I just showed you in the manual, use that manual from a specific manufacturer, right? Whichever one that is the one you're supporting. And by all means, find somebody you like, find somebody that makes good equipment and support them. Okay, this is a generalization when you don't have the information. That's what I'm doing here. Take notes. This will help you out in at midnight on New Year's Eve kind of thing. Okay. Confirm what the output of the boiler is based on the job specifics. We need to know what the input is. We need to know, is there any D rate for altitude, caloric value, or anything like that? A lot of times the natural gas utility will tell you what their caloric value is. Those who don't understand that is how many BTUs a cubic foot of this gas can produce at that given altitude. Okay, so that's what you want to. That's more accurate typically, because then you have something from the people who are selling you the gas and are putting the recipe together, so to speak. Okay, deduct for efficiencies based on the application. All that means is, what am I doing with this? Is this going to be low temperature? Is this always going to be condensing for the most part? Then by all means, you could use your AFUE number. Okay, if it's not, then use something less, right? For instance, AFUE is the 95, 96. If you know that thing's going to condense the majority of the time, you could use that number in your sizing. But if you say, well, I'm going to do a bunch of snow and ice melting at high temperature, I'm going to do a bunch of domestic hot water generation at high temperature, et cetera, where those return temperatures won't be as low as they could be on, say, a high mass radiant application, then don't use the AFUE. Use something less than, probably in the neighborhood of 86, something like that, just over the edge of non-condensing, that sort of thing. So anyway, again, the input of the boiler minus the altitude minus the efficiency will some sort of get you to the maximum output of the boiler, and you could size the pump on that. Now, here's what I want you to ask yourself a question. Is the boiler size bigger than it needs to be? John or Dave, where am I going with that question? How often is the boiler the exact size that you need for your application?
I had it once, but also later in that afternoon, I did discover a unicorn and was able to capture him. It was a great day.
All right, you see where I'm going with that. So here it is, real quickly. Let's take the same 155 at a high efficiency AFUE of 95%. So here's the math on that. 147,250 is the result of this calculation here, right? Divided by, I'm just going to use, just for teaching purposes, a 30-degree delta T. I take my 30 times 490 gives me my 1470. So that result of this divided by this, anybody want to spit it out real quick? Most people doing TACO webinars have their calculator handy. What do we get? Anybody?
Not seeing anything, Rick. Oh, we got 10. We got tens. There we go.
Okay. All right. Very good. I didn't give you long enough, but you see where we're going with this, right? Here's one, same calculation with less efficiency, and it slightly gives you a slightly less GPM required. If you're only going to be operating at 86% efficiency, then you don't need to size the pump for anything better than that, right? So again, 155, take this off of there, it gives you this. There's your delta T, there's your constant. You guys are used to 500, just keep using 500. Again, I'm splitting hairs and I ain't got any kind of thing. But for the most part, there's a reason that the number drops, and we talk about that on other webinars. Okay. Here's one with altitude. Some people say, well, altitude, again, if you get something from the manufacturer, you go through the steps of proving that you're getting a certain amount of BTUs per cubic foot of gas, then by all means. But like I said, if you get something from the people that supply that gas that say, hey, you're going to take a D rate, then be sure to derate that first. Your derate comes off of that. Then that 155 becomes a 130-200, and then you take your efficiency off of it, which gives you a maximum net output. And that's what you size the pump on. Here's that same math that I just showed you at altitude, okay? So you're 8.4 gallons a minute. John, this goes right to what you were emphasizing before. What if I wasn't, doing something as efficient, and I look at here, 0.86. That gets me down around 7 gallons a minute. Exactly what we had talked about on that last emphasis that you made. Okay. So anyway, folks, just understand these boiler circulators should be and can be smaller than you have imagined in the past. Again, to quote my friend John here, we often see the Benford 5000 as just a standard, a boilerplate boiler circulator. Okay, that'd be like our 0013. Okay, we've seen that as that's just a really big pump. And here's the kicker. Most of you folks have a real easy way of telling how big the boiler circulator is. And folks, the boiler manufacturer nowadays, remember I said they always are looking at the supply and the return of the boiler's heat exchanger. They're showing you what the delta T is. And folks, if it's not out there where it should be, turn the damn pump down. And if you've already on low and you're still at 10 and 5-degree delta T's, you might want to think about putting a pump that's more appropriately sized in there. Hopefully my point's made. So anyway, so in order to do this right, again, these are generalizations, not having the boiler's manual available on midnight, New Year's Eve, etc. Just we got to have to estimate what the pressure drop of the boiler piping circuit is at that given load. I'm showing you the load being 10 gallons a minute, right? Well, pressure drop of the boiler heat exchanger, if it's a water tube style heat exchanger, it might be 3 or 4 times this number. Okay, always try to look it up if you can get somewhere online. Try to figure out what it is. But these very popular fire tube designs are much lower pressure drop. They're just buckets of water that we're pumping water through. There's not a lot of resistance. And again, a lot of these manuals, if it has to be from somebody else that has a similar one, you could probably use that. In this case, I'm just under 3 foot ahead. As long as that boiler manufacturer did not add for the incidental pipe valves and fittings, then you're going to have to add for that slightly. But when it's appropriately sized, there's not, and relatively short, like most of the near boiler piping is on the primary side of a primary secondary configuration, then it's usually, a foot or 2 foot ahead, maximum. So again, we take things in consideration like, is there a magnetic dirt separator on there? Are there balancing valves that somebody has cut in there? That sort of thing. So you have to, that all has to be considered on that estimate. Okay. So in this case, I got a primary boiler circulator with a requirement of 10 gallons a minute at 5 foot ahead. Voila. I have the ability to come up with a circulator and make sure it's the right one for the job. Of course, I'm putting my best foot forward here with our 0018E for one specific reason. And again, just like I said, this doesn't have 0 to 10 or pulse width modulation yet. Okay, but what I can do with this, as I mentioned early on, is I can now appropriately set the GPM of this pump to what's correct or appropriate for that specific application that you happen to be working on. Okay, remember what we can do with the fixed speed mode of this pump is we can turn it up or down anywhere between 4 watts or 44 watts. Okay, that's what's cool about this pump. And a lot of our competition can't do that. They're still giving you 3 speeds under that fixed mode of operation. Okay, so again, we have just a dial on the pump that you can just, think of it like a volume dial on a radio or a dimmer switch or something like that. We can just turn it all the way low is low, 4 watts. All the way up on this pump is 44 watts. But what's more important and more popular is the fact that we can put it anywhere between those two that's appropriate for that job. In this case, let's take a look at it. This is what it looks out like without all those little performance curves at reduced RPMs. But, let's go in. We need 10 gallons a minute. Okay. And we estimated about 5 foot ahead. Okay. That's calculating a curve, a system curve, or a resistance curve for this to be something like that. That gives me an operating point that's beautiful. You know, I even got a room to go up, but more importantly, I got room to turn this thing down. Okay, and again, we'll turn it down when we get the feedback from the boiler manufacturer that gives us the delta T under a design load condition. So those are good. You go out on a job, you're just starting a boiler up and it's really cold and you got some really cold water coming back from a high mass slab. You can put that boiler in a design condition. That means the maximum firing rate it's ever going to see under a normal design condition, right? So anyway, that's what we want to try to simulate. Okay. Let's say you got a 0015 E3. It happens to be on the truck. It's midnight, and I can't turn this pump down to what it should be. Then what is the appropriate mode to use? Well, let's take a look at it, right? You can see here that we've got low is a setting of 5 foot ahead under a constant pressure type operating mode. Now, I gave you a caveat when we started here that this is not really the right mode to use, but it works fine as long as you're not anticipating this pump speeding up or slowing down, because it's going to find the resistance of the near boiler piping and the boiler's heat exchanger, and it's going to find its happy spot, and that's where it's going to stay every time it turns on, give or take a little fluid differences in viscosity, right? But it's very slight. Okay, it's think of it this way: there's not zone valves or telestats or actuators or anything that are going to change the hydraulics that this pump is ever going to see in a primary boiler circ application. Hopefully that rings true to everybody and you understand where I'm going with that. There's the medium head and there's maximum head. In this case, we knew we were at 10 at 5, and that's what you're going to see pretty much. It might move a little bit back and forth here depending on temperature, viscosity, and some other things, or how well you did your estimate. But the beauty is I can come back this way as well. Okay, it'll just find its happy spot somewhere along this line. So we're running out of time. I'm going to go ahead and just remind you of something that the reason we're emphasizing this, right? There's that same calculation we've looked at already. You see that where we got 10 gallons a minute. But what if the load changes? Remember, 10 gallons a minute was based on a design load condition. What if we're half of that? What if we only have half of the load, which is what these next numbers are representing, right? Then this is how to do the math to anticipate what your new temperature differential is going to be. You take the net and you divide it by your constant that you're using, typically 500, in this case 490, and then by the GPM that you originally designed at. Now we can anticipate a 15-degree delta T. So under a half load condition, I get half of my delta T. But at least 15-degree delta T is a lot better than 3 or 2 or 5, which is what we see in a lot of these conditions. And again, we want those delta T's to be as wide as possible at any given time. There are limitations there, like I mentioned, on bench conditions, etc. But for the most part, this is how to anticipate a fixed speed pump. Now, again, even if I'm using a circulator that has 0 to 10 and the boiler's controlling it, you can't ever go any lower than low. So that's why it's still very important to get the circulator sizing drilled in, get it pinpoint, dot your I's and cross your T's on this thing, because it'll pay dividends in the longevity of the overall system efficiency. So again, keep it as low as possible. That boiler supply temperature, this is a review. We've done this before with you. This is just a little showing you if I had a 140-degree temperature going out to the system and I designed it at a 20-degree delta T, that shows me my delta T across the system. The question is, what should I set the boiler up for so that I get this 140-degree out here when I actually have a blending happening here? It's actually higher than 140. How do we know how to figure out what it is? We're going to simplify it pretty much. We know that we sized it at 10 gallons a minute based on a certain delta T, right? In this case, it was a 30-degree delta T. So here's how the calculation looks if you want to take notes. The boiler supply temperature would be equal to the load divided by the boiler's flow divided by whatever constant you used based on the fluid type and temperature, right? And then you just add the return temperature. Okay, so that's what this would look like. Okay, 147,250 divided by the flow of 10 gallons a minute. My constant's 490. It gives me a 30 plus 120. 120 plus 30 is 150. Or even simpler, you just take the boiler's delta T, okay, that you used and add it to the system return temperature. So 30 is my boiler delta T that I used, and I got a return temperature of 120. 120 plus 30 is $1.50. And that's just for us folks that don't know how to solve for X. So
I don't know how many times I saw you explain that, Rick, before it finally clicked with me. I was consciously choosing the harder, more difficult, more complicated method every time as my
every
go-to method.
time.
But
I love it.
you taught me well.
Well, cool. Cool. Okay. Well, I'll turn it back over to John and Dave. Try to answer any questions if there are any. We've ate up all of our time, and but we said we'd stay on. So you folks that want to hang out with us a little bit, we'd be glad to do that with you.
There are a couple of questions that came up during the presentation that I wanted to address specifically that kind of really weren't part of the presentation. And one was, would you recommend hydraulic separators instead of closely spaced tees? And the answer I wrote to Brian, who asked the question, was it depends, right?
Yeah. Yeah.
And it depends on the size of the zones that you're dealing with. If it's just a single big zone or just a handful of zones where the BTU load of the zones are larger than the lowest firing rate of the boiler, closely spaced tees are fine, and that covers an awful lot of your jobs, right? So that makes closely spaced tees kind of your go-to method for ModCon boiler piping. Hydraulic separators really help when the zones are about the same size as the lowest firing rate. It gives you that hydraulic separation plus a little bit of mass. If you have micro zones like you might with a radiant system, where the BTU loads are smaller than the lowest firing rate, then you need to go to a buffer tank. And a buffer tank is really just a big mungo hydraulic separator, right? So that mass becomes really important there. It's never wrong to use a hydraulic separator ever. There's a lot of benefits there because it's made for you, so that saves a lot of time in your construction of the boiler piping, and it's compact, so you might not have the room to build a header. Maybe you want to save some space. So those are kind of the field options. It's never wrong to use closely spaced tees under the right circumstances, and it's never wrong to use a hydraulic separator. So it just kind of depends on what you're after, I suppose.
Yeah. Another thing to remember, some of the boiler manufacturers are still making condensing equipment that are high mass. So what does that do for us?
That's a big help.
That reduces our cycles, and it just it's the only reason, like John mentioned, we're putting a buffer tank in there. We're putting a buffer tanker in there to add mass to a low mass system. And we're saying, well, okay, well,
yeah,
what if I just put a boiler in there that's got the mass that I need? That absolutely can be done. And that's not a plug necessarily. Just remember, there's more than one way to skin whatever you want to skin. Okay.
There you go.
I don't want to offend any feline lovers out there.
Right, there you go. And then there was another question about DHW production means that the BTU of the boiler needs to be higher than the building heat loss. And there's a yes with an asterisk there, because it's not, A, that's not always necessarily the case, and B, if you can certainly, if the loads work out, there are certain workarounds there. There's a formula. If it's what the smaller boiler is going to do is affect the indirect rate of recovery, which is going to basically harm your first hour. It's going to lower your first hour storage, your first hour capacity. After that, the capacity is what the recovery rate is.
Yep.
So there are certain ways around that. First off, you do the math and find out what your rate of recovery is, and then figure out what you actually need in the DHW load. That'll help you make that decision. And then you can also offset that a little bit by storing, by using a larger tank, all right, storing more water and or storing that water at a higher temperature and using a mixing valve, and that'll extend extend your first hour rate. So there's ways around it, okay, rather than just saying, well, this is what the indirect manufacturer says, this is what I have to do. It may very well be. It may turn out to be that way. If you've got that no excuses, I got that 16-person shower stall, so me and my 15 of my closest friends can all shower together, well then yeah, you're going to have to need that, because you don't want to run out of water on those conditions.
Yeah, cold water is not a good thing in those situations.
No, definitely not. So anyway, let's see. Okay, well, we got a question here about, are you planning to give presentations on boiler sizing, especially for domestic hot water for different occupancy types? Well, it worked out well. Yes. Yeah, exactly.
We
yes,
will.
I think that's going to happen, Ollie. I absolutely think that's going to happen. And this one just came in from William Sherwin. It appears that using a variable speed primary pump that allows for setting up the flow by delta T versus old-fashioned flow measurement, the cost and time is much less, and the increase in accuracy is worth the extra initial cost of the pump. Yes, that's a statement we've been making for, oh boy, how long? I'd say almost 10 years now. Delta T pumping is by far and away the most accurate and best way to run any hydronic system. Delta T is part of the universal hydronics formula. It states that GPM is equal to BTUH divided by delta T times 500. If you want to vary the speed of a circulator, keep the delta T constant to what you designed the system to, which is not a crime. By what some people might say, it's not a crime. You give the system the delta T at which it was designed, and then the flow rate is going to have to change in lockstep with the load to whatever the circulator's low end capabilities are. And all circulators do have a minimum speed on them. So yes, William. If you made that comment during Takeo After Dark, we'd send you a T-shirt.
And Curtis also made the same statement or question. He said, what about using the VT 2218 as the boiler pump too? So Curtis had said that. Good job, Curtis. Yes.
I had one in my house doing that for 7 years almost. Almost 7 years. So 6 complete seasons. That was my boiler circulator, and it worked flawlessly on a condensing boiler, right?
Gotta love it. Gotta love it. All righty. Well, terrific, folks. Any other questions you have? We're happy to stick around, and this is a good time to ask them on Rick's wonderful presentation, or on really any other questions you might have. This is kind of open. This can evolve into open forum time for you. So any questions on anything hydronics or Takeo related, we're happy to try and to do our best.
Got 160 of you hanging around for some reason. So
yep,
fire away.
Well, thank you, Laura. Thank you for being with us. Appreciate the comment. Well, our group is bashful. Justin says thank you. Thank you, Justin. We appreciate you being here. And thank you to everybody else for being here. Again, a wonderful presentation, Rick. Well done, my man. And thank you all for being with us today and giving us an hour or so of your time on a Tuesday morning / afternoon, depending upon what it is, wherever you are. And we are going to look forward to seeing you tonight. If you are interested, tonight we will be doing a Takeo After Dark presentation on the importance of boiler water treatment. It is always a very, very popular presentation. That will be tonight, 9 o'clock Eastern, 6 o'clock Pacific time. You can register for that through on our website, takeocomfort.com. And in addition, tomorrow night, in our regularly scheduled Takeo After Dark, we will be discussing discussing an important question. With variable speed circulators all out there, is there still a place for the 3-speed circulator? I submit that there is. The other two guys may have their doubts, but I submit that there is, and we'll be making the case for that. And hopefully there'll be enough information there to help you out. But you can also register for that event on our website, takeocomfort.com. Click on the training tab, and you can see all of the upcoming webinars we have. And please feel free to sign up for them. We'd love to have you. And boy, oh boy,
Indeed.
and as you can tell, we have a good time when we do these, and we hope you do too.
Hey, just wanted to, got a couple of questions from a few people out there. They're asking about, are there any manufactured teas out there? And yes, I did send a link out in the chat section, and I just sent it out in the questions too. But we do have a closely spaced tea manufactured. You can't get any closer than this tea with your two teas there. So
Yeah, if you got any closer, the teas would be behind each other.
right. Oh wait, they are.
Yeah, wait, they are. Yes.
So actually, if you'd like me to share that, let me pull that up on my screen. I do have it up on my screen at the moment.
What's the smallest primary size that comes in, Dave? I forget.
I don't have that memorized myself, but I will pull it up on the screen for everybody to see.
What he's referring to, folks, commercially, we do something called load match. And this is kind of how we do a monolithic run of pipe around a building and pull off the secondaries. And the secondary would then, in turn, do a specific zoned area with a small pump rather than a valve and balancing and all the other stuff. So anyway, I can't remember how small it actually comes in, but that, yeah.
So
good,
here's
good
basically
picture,
what
Dave.
you're looking at. So
Yeah.
here's your 3D rendering of that T. So you have your secondaries coming off the top here. The different configurations are shown up down later in this piece of literature. Let's see here, and basically a whole webinar on what we just did.
Yeah.
And there we go.
1.5 inches is the smallest size.
1.5 inches.
Oh, okay. I'm sorry, 1.25 inches in bronze.
In bronze, okay.
We go 1.25 inches in bronze and sweat, and then we have 1.5 inches and 1.25 inches in bronze and sweat, 1.5 inches in grooved, 1.25 inches, and 1.5 inches in NPT. The
Very
smallest.
cool.
And they go up to 4 inch, 6 inch actually in grooved.
Yeah. Well, good. Thanks, Dave.
No problem. Little best kept secrets that we have sometimes. Like to show them off.
There you go. Yeah, it's a simple little device, makes it easy, right? And actually, you can't get any closer than in the same tee, right?
Right.
Yeah.
Alrighty, folks.
All right.
Well, hey, questions have dried up, so I just want to give one last thank you for spending your Tuesday with us, and we hope to see you soon. Hopefully tonight, tomorrow night, or any upcoming Tuesday afternoon. We'd love to have you, and we enjoy your presence. So thank you again for being with us, and thank you, Dave. Thank you, Rick. What a great presentation, and we'll see you all down the road on Takeo Tuesday.
Enjoy.
There we go, right here. Got to get him up, Dave.
He did it. He
There
did
you
it.
go. He did. That's right. All right. Take care, everybody.
Good day.
See ya.
Good day.